Here we have the most up-to-date table of all of our linear motion variables right next to their rotational motion counterparts. We've previously defined through torque. Within these last few videos, we talked about the energy for linear motion, kinetic energies measured in joules, and luckily for rotational motion, that kinetic energy is also measured in joules. That's what allows us to use that conservation of energy equation the same, just with this new type of energy to consider. And we mentioned its equation is the rotational kinetic energy is 1/2 I omega squared. All right. Our next big topic is angular momentum, and it is our rotational equivalent of linear momentum. Linear momentum, I went ahead and included the formula here for y'all. It is P equals mv, and remember our units for that are kilograms, meters per second. Angular momentum also has an odd variable that represents it. Angular momentum is L, and so L equals I omega is what that equation is going to look like. And our units for angular momentum are kilograms, meters squared per second. And so that is our next idea we're going to be looking at. And we're going to look at how kind of we end up with this relationship between net torque and angular momentum, just like we did with linear motion. First, we started with Newton's second law for rotational motion. That looks like this: net torque equals I alpha. And then we rewrote alpha, our angular acceleration. We said, well, that's defined as the change in the angular velocity over time. And then we expanded that out. So net torque equals I omega F minus omega I over T. And we could expand that out by distributing the I even one more time. So I omega F minus I omega I over T. And now each of these I omegas are our angular momentum. So we end up with net torque is equal to the change in angular momentum over time. And hopefully this looks familiar from our linear motion, where we found that the net force is equal to the change in momentum over time. So if we are changing the angular momentum, then we know there has to be a torque. A net torque is acting on our object over some amount of time from that equation. Net torque equals delta L over T. And so if the net torque is 0, that means that delta L is 0, which means that the angular momentum is conserved. So if there are no external torques acting on the system, then the angular momentum is conserved. And of course, that's going to look very similar to how it does for linear momentum. Or yes, we can say that the initial angular momentum will equal the final angular momentum. And depending on if we have multiple objects, that could be the sum of those initial I omega values for the total initial angular momentum, and it could be the sum of the final I omega values for our final angular momentum. And so that represents our law of conservation of angular momentum.